Hello class, I just wanted to make a video. I had a couple questions about some things that are going to be on the test, and then also to explain a little bit about some of the heat related things that are going to be on the test. So I just wanted to first show you guys some good things to use to help study. So I think our quiz that we did earlier is going to be a really good thing to help study. So if we go back to February 8th and 12th, we took a quiz. Our test is going to look a lot like this. So I have the answer. I made a video even, and I'll show you the video where we did some density equations. So our test is going to have a couple density equations, a couple questions about picking which would be the best unit. It's going to have a couple questions about converting in metric units, and some dimensional analysis converting, and then we're also going to do our heat stuff. So to kind of practice or help remember that beginning stuff or explanations, go look on February 15th through the 19th, day 3. This is where I made a video explaining how to do the first part of our stuff that we learned this partial. Now in terms of practicing for our heat equation and problems, the best thing to do is to go to day 4 of our review week and do our example heat problems review. So that's going to be our worksheet that's going to help you guys kind of practice doing this. But right now I'm going to kind of explain how it works. So I want you guys to try it for yourself and then do it. But I posted some answers here so that you guys can go and review and help teach yourself by looking at the answers. Don't just write down the answers because that won't help you for the test. But if you want to look through the answers to understand how to do something, that would be great. So for right now, we're going to focus on our heat problems. So this is going to be our answers from our review day 4, heat problems review. The answers are going to be here. So the hardest part I think about these kinds of questions is being able to write down what's given. So it is really good that we practice learning what each of our variables mean. So for example, let's read this problem. Mr. Justin makes a cup of coffee at, a cup of hot chocolate at 95 degrees. Mr. Justin doesn't want to burn his mouth, so he waits until it's at 40 degrees Celsius. The hot chocolate weighs 15 grams and has a specific heat of 4.138 joules per gram Celsius. How much energy is released from the cup while waiting for it to cool off? So when we're doing these problems, the first thing that I think is always easiest is to start with mass. So anytime we see grams or weighs, like here or here, we're going to be talking about mass. So that would be our M. Our CP is our specific heat capacity. So we can put that in for our CP. And then our temperature final, or our TF, is where we stop. So final is kind of like the end. So where we're going to stop, we're stopping at 40 degrees this time. And our initial is where we start at, is 95. So now once we have these variables already labeled, we can put them into some of our equations here. So let's look at the equations we're going to use. For this one, we're going to use our Q equals mc delta T. If we tried to use this one all by itself, just like this, we would have our M already defined. We can plug 15 grams in for M right away and be good. We can plug 4.184 in for CP right away and we can be good, but we need delta T still. So that's why we're going to use delta T is equal to TF minus T initial. So let's first use our TF minus T initial. So we'll do 95, or wow, TF should be 40. Sorry guys. TF is 40. T final is 95 degrees C. And so we get a negative 55. degrees C. Negative 55 degrees C, which is great because now we have our delta T. So once we have our delta T here and here, we can plug it into our Q equals MC delta T. So that's all I did in this last step. And then I simply just multiplied them all together as 15 times 4.184 times 55 degrees. For our second problem, we're going to be trying to find our specific heat. So we're trying to find specific heat. This one says Ms. Brenna is drinking 10 grams of liquado to cool down on a warm summer day. If it takes 500 joules to warm up the ice cream from 3 degrees Celsius to 23 degrees Celsius, what is the specific heat of the liquado? So again, the hard part is finding what's given. Anytime we see a J, we're going to be doing Q. It's related to Q. So anytime we can see a J for joules, we're going to be talking about Q. So Q is 500 joules. Mass, well, right away it says is drinking 10 grams. And remember, grams is mass. And then we end, our TF is where we stop, is 23, and TI is where we start, which is 3 degrees. So we end at 23, start at 3. And now this time we use a little bit different equation. Our first equation, we're trying to figure out how much energy is released. This one, we're trying to figure out what our specific heat is. So when we're trying to find our specific heat, we're going to use this equation. Cp is equal to Q divided by M times divided by M times delta T. And so just like before, if we wanted to just use our Cp is equal to equal to Q divided by M times delta T, this one, we would still need delta T. We could plug in Q on the top, we could plug in M, but we need delta T. So that's our first step, is having to solve our problem. So we have to take our final minus our initial. So we're going to take 23 minus 3 and have 20 degrees C. And then we can now plug it all the way in. Now we can say 500 joules divided by 10 times 20, and then we get our answer to be 2.54. One note, when we're putting this in our calculator, we want to make sure we have parentheses around this part. Otherwise, our answer will get kind of wonky. So make sure we have parentheses here. All right. This one is very similar. We have, oh, our thing got cut off. I'm going to do it this way. Number 3. So Mr. Max is worried about his length of his wooden meter stick changing height when it gets really hot. He wants to make sure the stick stays at exactly 1 meter. The temperature changes from 50 to 30, and the expansion coefficient of wood is 3 times 10 to the negative 6 meters per meters cubed. How much does the meter stick change in length? So again, the hard part is finding our givens. So our little fish is called an alpha, and it's actually A in the Greek alphabet, so alpha, and that is related to our expansion coefficient. And our alpha is always going to be very small. We can see that this number is 3 times 10 to the negative 6. It's another way of saying 0. It's another way of saying 0.00000603, like this. So it's a very, very small number for our alpha. So anytime we're doing these kinds of problems and we see a small number, that's going to be our alpha. Our starting length is our L0. Our starting length, and we're going to say that is 1. And then our temperature is going to be the exact same as it was in our first other examples. We're going to have starting at 15 and going to 30. Initial is 15. Our final is 30. F for final. And then we get to use our equation. So if we look up here, if we have a delta L, if we have alpha, if we have L sub naught and delta T, we're going to use this equation. But this time we don't have delta T, just like we didn't have delta T in number 2 or number 1. We need to find it. So first step is to find delta T. So we're going to take 30 minus 15 for delta T, and our answer is 15. Now that we have our answer 15, we can plug everything in. We can plug in our alpha, which is 3 times 10 to the minus 6. We can plug in our L, which is 1, and our delta T, which is 15. and we get a really, really small number in meters. So this says that our change in L is going to be very, very, very small. We're really not going to change much. All right, let's look at this last one. I'll make it its own page. This one is the longest because it's kind of like 3 problems in one. Wait, I want to insert, sorry, page break. That's what I want. Cool. So again, hardest part is finding the right numbers out of all this. And so this says how much heat is required to change a glass of water with a mass of 12 grams starting at 75 degrees C to a gas at 100 degrees C, given that the specific heat capacity is 4.184 and our heat of vaporization is 2,230, 1 mole of water, and water vaporizes at 100. So if we walk through this, our M is going to be 12. Our heat capacity is going to be this similar, is this 4.184. Our temperature final, where we're going to stop at, is 110. We're going to start at 75. And this T vaporization is a new term, but that's where water vaporizes, which is going to be 100. And then the last few things, we have our delta H is our heat of vaporization, and we have 1 mole. N stands for the amount of moles. So the idea is we're going to break this down into 3 steps. So we're going to use 3 different equations. We're going to use Q is equal to N times delta H. We're going to use Q is equal to M times Cp times delta T. And then delta T is also equal to T final minus T initial. But how we're going to break this down is we're going to do step 1. We're going to go from our initial temperature until we go to our vaporization temperature. Step 2, we're going to change all of our water into gas at our temperature, so we're not changing temperature. Step 3, we have to go back and change temperature again. And then step 4, we just add them all together. So we're solving for Q in each step, and then we'll add them all together at the very end. Now, step 1 and step 3 are going to be incredibly similar to our very first problem because we're going to use Q is equal to MC delta T to find them. So we already have M. We're going to use M times Cp delta T. We already have M, we already have Cp, but we need delta T. So the only tricky part is here we're going to actually go from T vape minus Ti. So we're going up until we change our phase. So we're going to do 100 minus 75. So we have 25 as our delta T. We're going to use 12 and 4.184 for our mass and our Cp. And then we multiply them to get 1,255.2. For our step 2, all we're going to use is Q is equal to N times delta H. So all we have to do is look at our delta H and our N and multiply them together. So we're going to do 1 mole times 2,230 joules per mole. And luckily, because it's times 1, it's really just itself. So we have 2,231 joules. The third step is a lot like the first step. We're going to use Q is equal to MC delta T. But this time, we're going to go from T final to T vape. So this is actually, I should write it like this. T final minus T vape is 110 minus 100. So our delta T is going to be 10. And then once we're going to use the same mass and the same Cp that we did for step 1, and then put in a new delta T, multiply them all together and get 502. And then the last thing we're going to do is add them all together so that our final answer is simply just this. So I hope that helped. So for some more practice with maybe some of the different terms, I made this good little heat equations game, which is just asking like what does N stand for, and Q is equal to N times delta H, or different things like that, which is also going to be helpful to learn some of those terms. But if you guys have any other questions, please let me know. I am here to help.